So let's start with uh, I think so. We left it here last time. The self we had to do cluster fit and PIRL. So I will be doing them first, and then moving on to the trucker problem. Let's quickly go through the cluster fit through the slides. It's a pretty easy one since I had given the basics of what it represents. Uh, so let's try to recap. Uh, Self-supervision, pre-training, what it is, a variety of downstream tasks, which where we learn from a representation. Uh, this is a classification task. This is supervised data set in which we have trained it here. And what is self supervision? It's kind of a semi-automated, and it will try to uh, have uh, a kind of a self uh, uh, annotated uh, scheme that can be used for labeling images or objects in it, or videos or other complex representations. Uh, this is with respect to the uh, medical domain, and how and why is it useful here. So it's, uh, this is what how they how Ishan defined it. Then supervised, unsupervised, and self-supervised with respect to some other co-occurring modality. Uh, then this is an example of that being applied in, how do I say it, word to vec, that is NLP. Uh, And these are the representations for the success in birth, which had many downstream tasks. Then we go to the context of the computer vision. Uh, these are the pretext tasks, which can be used for learning representations. Here we will talk about rotation and jigsaw based puzzle tasks. Uh, so this is 8 or a 9-way classifier in which you have a uh, uh, blue box, and what it is trying to do by context prediction, trying to learn the different relative positions of the patches. So this was it. This was the input, the relative positioning, and the random initializations, and the with respect to the ImageNet, AlexNet. Yeah, this was simple. We discussed it last time. This was the pretext. Sorry, with respect to the rotations on the predicting image rotations paper, then the colorization example which we discussed, then the image in painting. And this is using a video to get the self supervision, and we have to fill in the blanks or track the objects and predict their positions here. So this is shuffle and learn, which is trying to uh, as the name implies, trying to get the frame of uh, a, uh, a particular middle frame that is there with respect to the images. from starting to the end. So if it is the third frame or the fourth frame or the nth frame in the 0 to n plus 1 or 0 to nth frames, what's the temporarily correct order of the video in a frame. So this is also important. Can this frame lie in between? So this was with respect to the three-way classification task that it performed on. This is with respect to the nearest neighbor query frames. Then this is fine-tuning on human key point estimation. Then this shuffle and learn on the ImageNet supervised shuffle and learn datasets. So yeah. Then the odd one out networks, the wrong order and the correct order. This was other paper that had implementation of a kind of a process in which you have uh, a correct order and an incorrect order. It's much like the contrastive, or you can say the semi-supervised, uh, like approaches in simpler, for example. Uh, how do that affect it? And so it will try to determine the correct order based on the predictions. So it will try to give the odd one out of uh, in a network. So this is just with respect to video. Then we even looked at the deep visions. Deep Mind's audio visual co supervision example, in which the sound and the uh, video that corresponds to network. So how do we do that? A couple of networks that can go side by side to determine that. We looked at the uh, uh, architecture and delved in a bit. This is that. Uh, yeah. Then there was a cool animation with respect to how it is all represented and what's the downstream task it can be used for with respect to deepfakes and stuff. So yeah, we discussed that too. Then what would make this sound? So if you have a saliency map of a piano or a flute, how will that sound based on the object that we have detected? So it will uh, try to predict this or try to correct it based on that. So there are many applications of this. The pretext, then we had gone through the pretext, the relative position, the correlation, and the combination of two for the multitask. This is a multitask objective that we talked about last week too. This helps in representations, and uh, as you can see from the numbers, uh, then information predicted varies across tasks, 8 possible locations, from less to more. Uh, how do we do? How do we proceed? And what's the metric that? What's the how do I say it, the actual pretext? How do I say it? Technique. If I may be using a wrong word here, but which component or which technique matters to improve that downstream task. Kind of a fine tuning based experiment which we can uh, which we do in Kaggle or other uh, uh, open source implementations. Yeah. Then this is with respect to the pretext. This is rotation. This is jigsaw. The contrastive, which we try to predict the image transformations here, and the patches. Then in the generative too, we can use this with respect to autoencoder via GANs, the ByGANs, which predicts more information. So that's the stage. Then this is with respect to the scaling, the jigsaw puzzles, uh, uh, and how can we scale them. As you can see, there are three permutations which are done here with respect to the image patches, and it classifies. This is a nine-way uh, classification, which each patch is has to be inputted through the network. Yeah, it's a nine-way. It's the nth way, n-way coordinates with the shared parameters. Uh, yeah, so this is where I think so we uh, reached till last time. Then we'll take it from here. This had the evaluation. We discussed about this too, and the last part with respect to the fine tuning versus linear classification. Why do we do fine tuning, and what's linear classification good at? Yeah. So here I was trying to give a representation of uh, I could select my, yeah. So here, if we can take this linear classification block as this, and we can divide it into subparts. So think of the linear classification block as the size, this guy. Uh, then I was giving an example of how fine tuning and the combination of fine tuning and linear classification can be used. So this guy, this guy, this guy, this guy, and this guy. So you can think of it as five, 1, 2, 3, 4, 5 sub blocks. And yep, this information can flow through the different, if I say the replications of this. Uh, this so you can say this is being replicated 5 times. 5, 4, 3, 2, 1. So, yeah. So this will shave off, I think so, minimum 8% of computation. So you can use these two together, the fine tuning and the linear classification layers. Uh, this is not called linear classification, it's called routing kind of a network. And yeah, so this is the state of the art which we do. Okay, so any questions? Please feel free to jump in. Cool. So now let's move forward. Okay. Then the evaluation across many tasks. This is image classification, few shot learning, object detection, 3D understanding surface normals, the navigation in this is specifically in a Gibson environment. Yeah. And then the evaluating the representations. This is the fixed features that they extracted, uh, which I alluded to. You can have a visualization in the excellent distill pub. You guys might know about that. You can see the extracted features at every level and how is it used for developing from the pixel, the lines, motifs, objects to a higher level. So that's 4 or 5 levels that we had covered at the starting. You can see the fixed features there. Then we can evaluate the representations based on the classification task. So yeah, this is that guy. Then increasing the amount of information that is predicted. This is map. Uh, mm, it's simple. This is the linear classification on the walk O7 dataset, present 50 and the AlexNet. So the number of permutations with respect to the number of parameters a network has. This is fast R CNN. These are mm, the techniques that they have used for video, and as we have talked about earlier. Uh, then in this object detection, if we used Jigsaw, this is self supervision, and this was supervised. So this was a difference, fine tuning all. Then the surface normal estimations, uh, including supervised PSP nets, training only the last few layers, input and the output. Mm. And you can see the differences here. It's minimal, really. Outputs, image nets versus the Jigsaw flicker. Then we had a few short learning, in which we compared this ImageNet with Jigsaw ImageNet and the random based learning. And what's the difference here? So it's catching up, as you can see. Yeah. Uh, then what does each layer learn? This is with respect to the interpretability, with respect to the linear classifiers. What is missing from the pretext or the proxy task? Then we had the rotation or the jigsaw puzzles, which we will go through quickly because we have to generalize that across those tasks. Uh, this requires pre-training and it's being applied to the transfer tasks as well. So uh, pre-training might be this is a kind of a task with respect to the hashtags that we give on social media. Sun, no filter, tree, fun. So it will relate these hashtags to the image, and this kind of a pretending how it helps. Uh, there are multiple research papers regarding this, and if you go to there are multiple videos that go into the technical depths of each and everything. I think we will go through PIRL too if we have time. About the semantics and non-semantic tasks produce good features. Uh, this is with respect to the generalization. This is with respect to transfer learning. Ah, then this is simply the hidden layers that do not generalize. The pre-training features should represent how images relate to one another. The nuisance factors, robustness with respect to objects, lighting, and exact colors. So this can be made robust from uh, argumentations, and the other kind of a pre-training, as we have just referred to here, jigsaw and rotation, clustering, and contrastive learning are the two ways to achieve the same here. And we look at two papers in the CVPR 2020, cluster fit and PIRL. Uh, this was by Jan and Mishra. Cluster fit. How do images relate to each other? This was the main idea in which they discuss the feature clustering. Given a label, how to we represent those images, like in k-means with the clusters, and fit the predict cluster assignments there. So these are the two ways in which we do it. Uh, NPRE and NCF. If I go quickly to the research paper. This is with respect to this. We have discussed this. We are here, feature clustering, pre-trained networks, gaming clustering for performing the features, which becomes a label. And the second step was to predict the pseudo level labels of the images. These are obtained to the first step through clustering. So yeah. Then we go through the application in the downstream tasks. And pre-training on our data sets to get the pre-trained networks of NPRE. So yep, we can see the pre-training objective and then how it is being applied here. To generalize the clusters, here we are generalizing it in this part. And then we kind of use those clusters to fit a particular um, um, manifold. So it's you can also think of this as a kind of how do I say it? I go down here. So this is the pre-training step and the transfer learning step. Why do this work? Was the framework that they this also let me select text. So this is the cluster fit objective, and why does this work is because it leverages the underlying visual smoothness in the feature space to create a visually coherent clusters. And how does this do that? Then the clusters followed by the fit weakens the underlying pre-training objectives specific bias. So this is what's being done underneath the hood with respect to those two tasks that we have seen. First this and then this. So clustering than transfer learning kind of task. And we can view this from an information bottleneck perspective too, where the lossy clustering step introduces a bottleneck and removes any pre-training proxy objective biases that it has. So this is with respect to the online data and the data in an online settings, which is corrupted or the variance is too high. So we are kind of reducing the variance here to cluster it in a specific manifold, a specific part of a manifold. And that's the basic thing. And these are the results, the observations, and the steps that we do. So that's the basic part of it. We can go through the paper in detail if we have time. Or if you guys have any other queries, please feel free to jump in.
So basically, a lot of research coming from Facebook kind of develops these ideas, right? So they use this clustering objective in latest papers too, right?
Yep, because you can. I do not know about the newest papers. I think so. I will have to go through the uh, uh, yeah, the self which have they used cluster fit in, because this was in CVPR 2020. Maybe the derivative of this work might have occurred in the semantic uh, updates that they are doing, or uh, there might be some works that are under wraps, so we might not know about them. But yeah, I think so. This because this kind of objective, that's weekly's supervised objective. It's common for the social networks like Facebook, Instagram, and Twitter, because they have so much data. The uh, 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 images that we upload, uh, and we hashtag them. So they use it all, because the policy that you give, you sign on. So they have the full authority to use your data. That's why it's kind of scary of uh, 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 why Facebook is able to kind of know about you in such a how do I say it, in such uh, 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 good way. I can say it's the precise way by which your next step will be predicted. So that's one of the reasons. Yeah.
And interestingly, like basically this availability of lots of unlabeled data and a lot of compute kind of shapes the direction of AI research nowadays, right?
Yep. Yep.
Because like best most of the like or significant part of the best researchers go to Google or Facebook or some other company with a lot of compute and a lot of data,
Yep.
and basically their goal is like to leverage this lots of data and lots of compute, and they don't really like need maybe to make this learning as very efficient in like low data and low compute regimes. So that's
Yep, totally agree. And with respect to the how do we train it, how do we scale it, because you have so many images, you need to perform those gradients have to be accumulated, back propagated in a clear and awesome way, in which to properly utilize your end-to-end stuff. So uh, with respect to your compute and the network, so network of the GPUs. So yeah, those two things are necessary. But yeah, if we talk in the detail, those distillation steps are also important, and they have given a reason as to why distillation between what's the difference between the distillation and cluster fit, and this was the difference, and they have used softer uh, in cluster fit. They do not care about the label space, which of how your manifold has to be controlled, or your latent space, how it is being represented. But in model distillation, you use the labels to of the network to predict just in a softer fashion to generate the images. But the problem here is there might be too much. Uh, how do I say it? Mm, un unclear data, unclear labels. Uh, what unclear mean? What unclear means here is they kind of mm, have some errors, and how do you fix those errors? Those can be fixed using some sort of energy based methods, in which you try to form a fine line between the different classes of images, or the in the label space. So uh, that's uh, a kind of a difference. But yes, this distillation technique in which they have compared is a pretty naive implementation, which can be improved. But yeah, cluster fit is currently, I think so, the go-to technique that they have used here. Then we have the performance with respect to the Jigsaw pretain, the pretain 2x, and the cluster fit. And yep, as we can see, this is the +9, +3, +5, and the +7, and the different data sets. Gains without extra label, without extra data labels or changes in architecture. So yep, these are the performance differences that we have used in self-supervised learning. Uh, okay, so this is with respect to cluster fit. And why does cluster fit in the slides? Why does cluster fit lose a bottleneck? Information is transferred. The label noise and measure the transfer performance. This is with respect to the robustness, uh, synthetic noise. This is being applied to a fully supervised, weakly supervised images, videos, and a self-supervised with respect to the Jigsaw and the rotation networks. What were the results there? It's simple, really. Please ask here or in the Slack if you have any queries. No, moving on to PIRL. This is based on
So I
yeah.
have a quick question. So you think it's a good way to look at clustering technique, like to start, or is there like better papers at this point?
Yeah, there certainly maybe. Let me try to find the. Yep, they
Nice.
are. Yep. This is. You can go through so many papers because they might have improved it. I do not exactly know right now, but yeah, I will get this in the Slack if I find any papers that uh,
Thank you.
have improved on this technique. Okay, so yeah, then we go on to pretext invariants representations (PIR). What is last of it? What's contrastive learning is? Uh, so this is with respect to the contrast of. So if we have a group of related or unrelated images here, we group them and pass them through a network like Siamese nets. And we push them and uh, push the points that are together and push the points that are apart uh, based on the image features. And yeah, we get a kind of loss function that can be represented in a high level like this. So it's the same uh, embedding structure that we look at the word to vec. Uh, Initially, this is uh, kind of a derivative of that work. Mm. So, yep, these are the features. How are they pulled and pushed? Yeah, contrastive methods. Here we can use a energy-based objective too. So, uh, sequence. This is with respect to tracking objects, nearby patches or the distance patches of an object. The related positives, the unrelated. This is patches versus yeah. These are the kind of works that have been done here. The data argumentations that have been applied. So if we go through this, these are a kind of some pretext tasks that contrastive learning has been applied on, and semi-supervised methods that have been used here with respect to the CPC, which is contrastive predictive coding. Yep, this is the signal that says in the time space it's being unrelated. And this is in a speech domain, video or a text or a particular image. And yeah, so this is basically with respect to unrelated samples. Tracking objects here. This is unsupervised tracking in videos, Siamese triplet networks, and ranking objectives as we have just seen. These are the kind of argumentations that are applied and compared. So SWAV and I think so. Barto twins. Those were two works I that have come out recently. And they do that too. So, but they used a kind of negative uh, representations. And Barto twins, they compare on this kind of objective, the distance in a feature space. So those are the two works which recently came out. And, then different poses of object cycle. So this is with respect to tracking in video, or this is a derivative of, I think so, the faster CNNs. Uh, mm, then what is this? Then these guys talk about the nearby versus the the distant patches of an image. And this is the CPC V1 and the V2 methods. What they do here are called the positive and the image patches, uh, which with the goal to minimize the contrastive loss. So this kind of downstream task is used. This kind of learning is used here. I think so. This was here. Yep. This was used in PIRL here. I mean the paper that I've just opened up, and Simplia and Moco 2. Moco V2 had some improvements upon this based on the techniques of uh, contrastive objectives that they used on. So if you want to delve deeper, we can go there too. Art. Okay. Time. Then this is the color chattering and removing the colors. This is with respect to how do I say it? Random patches that basically becomes your negative. So you can compare this to the task with respect to the contrastive learning, and if we use the memory-based approach or a batch size that is larger, how will that reflect your overall training space? So there are different downstream techniques of doing the same thing more efficiently. Yeah, but this is a batch extraction problem. In Solve, they have used the negative patches too, so to make it robust. So that's one way to. Then we talk about the underlying principles of the pretext task. This is specifically with respect to PIRL. With respect to low-level representations, uh, how do we perform it in a three-dimensional uh, 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 way, in which if you try to uh, hmm, how do I say it? With respect to the different pretext, the pre-training pretext task that you had, how do that cumulatively affect the standard cross entropy or loss that you had? So uh, mm, this is what they truly talk about in this whole paragraph. But you can fine tune it based on the particular downstream task that you want, based on the architecture or the training on the signal to noise ratio here. So this and uh, was also one important task. Then they talked about Swift here. Swift is a kind of a handcrafted features that are inserted. Scale invariant feature transform, uh, like the Swift and the Hog or the HAR based methods, uh, to which are trained to be invariant to how do I say it? Different which can make those downstream tasks a bit faster. So yeah, or might help in the improvement across the particular task. Like in, I think so, there was a task being based on the self supervised GAN training, in which they used some handcrafted features for uh, uh, I think so 2 to 3 percentage points improvement. So you can use these uh, as a training objective or a kind of a robustness parameter in that space. So that also works. The this then now we go on to PIRL, and so this is pretext invariant representation learning, feed forward to uh, the idea is you want your representation to be invariant or capture as little information as possible of the input transform. So this is what it is about. And this is the sampling, the samples, the I and the I of t. And this is the transformation that they have done. And if you use contrastive learning, then the saved features VI coming from the original image I, and you have the features VI of t coming from the transform version, and you want both of these representations to be the same. And so they kind of train it with respect to this kind of contrastive loss. And this they use the jigsaw and rotation methods that they have discussed, and this had a multitask. You can also see this as a multitask learning. Uh, this is at a high level, but if we want, we can go through the depth too. And using a large number of negatives, yeah. This is the discrimination from the 2018, which introduces its concepts of the memory banks. Yeah. So he talked about using memory banks versus large batch sizes, and which is necessary in which condition. And when you try to model and data parallelism in a space of, I think so, in a uh, cluster of TPUs, for example, how do you actually train it? How do your model or data parallelism works there? Because this requires too much memory to train. So, feature vector per image in a memory with respect to the contrastive approaches that we have. Uh, and they talk about this in the slides too. Now this works. I transpose should be similar. This is some other stuff which is unrelated, negative. So simply test it and do those uh, small networks. It's kind of a inception blocks that you can see here. I think so they have used inception. If I'm not wrong. Yes. Methods. So it is this. Yep, Resident 50. So yeah. And then we go on to how it works. So yep, feature similarity, dissimilarity between those features in a memory bank. And yeah, uh, this is simple. This is the NCE loss that was given in 2010. So it's a improvement over that basic NCE loss. Um, yeah, so then they talk about the evaluation on the object detection tasks and the semi-supervised learning. So these are the results. Uh, Evaluations on the linear classifiers. This is the CPC V2. Simply so on. Yeah, this is 662, 63. Then in the wild, evaluation of the YFCC images, semantic features. This is with respect to the features uh, at each layers. Uh, they kept increasing for the different layers of both PIRL and Jigsaw, but dropped at the fifth layer for Jigsaw. So mm, this is the quality that's being represented. So yep, you can see the results with respect to the architectural because they have used negative sampling to a bit of so that's what the gradients here. I think so. If you backpropagate, then the training on the layers, the top 1% accuracy drops here. So for the Jigsaw, but increases for PIRL because of this loss objective that they had. Then we look at the scalability. Uh, uh, so yeah, Then this is Jigsaw plus rotation and only rotation. So these are the shortcomings. Yep. Please feel free to jump in. This is with respect. These are the questions.
So this Pearl paper, it was before SimClear, right? And
Yep.
in SimClear they used a different set of augmentations, which worked better for them. And like, do you think the set of augmentations they use is the most important difference here, or something else might be like?
No, I think so. This is with respect to the global and the local view. So these are the filtrations that they done, the argumentations that they used in Simplia, that they mostly focused on our argumentations, but they didn't use the negative sampling. I think so that this wasn't based on the negative uh, objectives. They only focused on the maximizing the agreements. So, with respect to the related views, so yeah, here this is just with respect the improvement here was just with respect to this loss, which totally was defined on the basis of the argumentations that they had. So
Are you sure that SimClear didn't use negative examples? Because I thought that was BioL was the first paper which achieved like good results without negative samples, and SimClear was before that.
no, this was anti Zent or negative 10. The examples that I don't think so. They used negative examples in same simpler. We try to, because Swarm has used them and they had the results. We compare it to Swarm 2. Supervised. Yep. In Swarm, they used compute codes and the negative examples. Hmm. Plus, they used a multi-crop strategy. So, yep, there are different versions of it. But I think I'm right in these terms. So, yeah, contrastive visual. Yep, we can take a look at it, and I will confirm my theory in the Slack too
Okay,
afterwards. But yeah,
great, great.
yeah, yeah. This is self-supervised learning primitives, the generative models. Mm, Then distillation. They ask about software distributions. Uh, this is a kind of a trick for training with respect to label smoothing and there are a couple of more tricks that have come out in recent times, as I've alluded to, they increase this distributions with respect to the classification of those labels. So these are all the things. Cool. So let's now quickly move forward. Okay, I've already taken an hour. Now let's move on to the trucker backer upper. It's a cool self-learning controller problem. And let me so this is the problem and how they have defined it. The goal of this task is to build a self-learning controller which controls the steering of a truck. Let me try to visualize this as well. So this truck can only move in the backward direction. So the point here is to move this point, which is called, I don't know, what is the a term for this? Yeah, the back of the trailer. This is the back of the trailer, and this is a truck. This is the front of the truck. This is the back of the truck, and the goal is to simply dock the back of the trailer to this point. That's the docking station. So this is from a upper presentation. Let me try to rotate it. Yeah. So this is the view from the upper point. So let me try to try. So yeah, this is from the upper point. This is the positions here. The X cab, Y cab, X dock, Y dock, X trailer, Y trailer points. This is the angle, trailer, and the cab. So the position, try, as you can see, what it's trying to do. So I think so. This gives a visual and quick, intuitive representation of the trucker problem. Trucker backer upper. So the goal of the controller here is to select an appropriate angle. That's phi at each time k. Here, this time is being represented from 0 to this point, which is 0 to k. And this where after truck will back up in a fixed small distance, so we can increase the sim speed and the steering angles. So as you can see, it has backed up to this point here. So we can spawn it in a random position and see how long it takes to back it up and drive using the controller. So this is the visualizations. The goal is to the theta of trailer should be 0. That's the goal. should be the back of the trailer should be as close as possible to the X dock Y dock point. So to this red point, it's as simple as that. These are the visual kind of geometric representations for the visualizations that they have shown here. Yeah, we calculate the change of angles and the position. This is the tan phi. Here, uh, theta zero is this angle, which is represented by S over L, the length of the car, and the S is here the mm, mm, signal speed, and the negative and phi is the negative steering angle. So signal speed here represents the you can say this kind of speed. So if I increase this,
I have a question in this diagram. Because they fail to label which is the cab and which is the trailer, because it seems like the long L thing that they put there is the cab and the other is a trailer. And if so, the scale of the drawing actually confused me.
yeah, the cab here is the small part in the front. So it's in, and this is the trailer.
Right, but that's correct in the right diagram. What is it in the diagram in figure 2, which is the part that confused me?
Oh yes, yes. It's a bit confusing here.
Because there it
yeah.
seems to be that the long part
Mhm.
is actually the cab. It
Mhm.
seems, I'm not sure, but
Yep.
then, they seem to have flipped, because typically the cab is small and the trailer is long, but that diagram without the labels
Mhm.
threw me.
Yep. The thing is, this paper came out in 1990, so at that point, uh, this was the best possible visual representations, because this is completely based on uh, uh, those basic principles of control, uh, and at that time, computer science wasn't uh, field, so they have completely represented in those mm, notations. So it's a bit of how do I say it? Tough to look at, because uh, we do not have uh, mm, the same viewpoints, but with respect to the uh, uh, education that we receive nowadays. But yep, so it's a kind of classical paper. So then this x dot and y dot is the s cos theta 0 and the s sine theta 0. These are the four parameters which is represented by the state: x cap, y cap, theta 0, and theta 1, because the length parameters are known. And this x trailer and y trailer is determined by this guy here, the Cartesian of the back of the trailer. We try to. Yeah, so this is a much simpler way to represent this. train controller. So if we look at it, there are, we go to the, yeah. This guy. This is the step of the state updates that are being done with respect to the time. This is the yeah. As you can see, this X and Y and theta0 and theta1. These are the state updates that are being performed here in the code. At each step, this is the reset, which is the initial steering angle, the direction of the initial car and the initial tray trailers. This is randomized here. Then this is the initialization with respect to, I think so, the y-ticks and the x-ticks that we will see this diagram. And how can we represent this? The sample plot of the environments and the going out of boundary, reaching the dock and driving into itself. It's kind of cool, jackknifing. Then the trailer XY is jackknife. These are the various methods. If off screen, valid, draw, clear. This is with respect to drawing of those patches here. This is simply, they have used this library, I think so. Matplotlib lines 2D to draw this and fill a rectangle with this guy here. And these are the trailer which they have drew. Then we can see. So this is the initialization. And the truck display is true, as we can see. If we reduce the degrees to radians, if I do here 10, you can see at each step, that's the movement. Close the run cell. So you can see at each, if we improve this by 90, suppose. So this is jackknife in this case. So yeah. So this is the difference that you can see. Then the next thing was, this is the steering angle. This is what I just played with. These are the end situations. Then we look at the training of the neural network to be an emulator of the truck and the trailer kinematics, and training of neural network controller to control the truck. So these are the two stages. trailer truck kinematics uh, which has been let me try to give a representation of the 6 dimension state at the time which is being used here. 6 dimensions. This is the state size 6, steering angle 1, heading units E, emulator. This is the sequential network that we form, the linear steering size, state size plus heading units. ReLU, then followed by this. And we use an SGD, the MSC loss. So if we try to train this, this is the kind of data set that we have constructed in this cell. And here we are forming a emulator. This emulator is being trained here. This from this data set that has been generated, we have 80-20 test stream split here, and we have inputted this data set into the tensor outputs. The tensor inputs and the tensor outputs with this mean and standard deviation. So this is the code representation, and we can see the inputs and the outputs. This is the tensor inputs and the test size, 593 and 474, and the tensors. Then I think so. This is being represented here. If I go to the the states here. So how do they represent the state here? This is with respect to the. Let me try to annotate. These are the 6 dimension state. So these are the signals that are propagating. This was initial representation of the 6-dimensional state vector and the steering angle that they generated to generate a new 6-dimensional state at time k plus 1. So this is the steering signal, and they generated this here. So this is the details of the emulator controller, which we can see. I think so. This gives a visual representation of the details of the training and the architecture that they have defined. Okay, let's now move forward to the emulator. Emulator is the emulator stateful diagram. This is with backward propagation. Okay, let's now move back here. This is the current location of these parameters 1, 2, 3, 4, 5, 6. 6 parameters plus the steering direction as input, and these are the outputs at the next time steps. And it contains the linear hidden layer with the ReLU, and the linear output layer. We use the MSC and train it as a stochastic gradient descent. So yeah, this can also be thought of as this guy here. Okay, I'll try to 200%. So this is a visually intriguing way to represent those initial RNNs. This I have taken from the video. This makes a bit more sense to me because it's unrolled. And we can see this representation using the emulator on which it is based on. This is represented here. This is with respect to the controller. C and the T blocks here. And
my question. I think he mentioned that it's slightly different from an RNN, right? Do you remember what he said?
What did he say here?
I think
it says
Gautam,
no input at the bottom.
Yeah, that's one thing. The other thing is, in an RNN, the number of stages is fixed, right? In this case, that's not the case. The H0 to HK, the size of the net, what we typically think of as kind of back propagating through time, the through time part varies in this case.
No, even in an RNN, it's not fixed. You can have variable length sentences, variable length time series.
But we would pad it, right? Typically. In this case, there's no padding. The actual network size varies.
Padding is only for the purpose of batching. If you are doing it separately, you can have it as any length as you want. It's only when you are batching it, you pad it.
Yes, but the point is that in this case, the individual each time or each what I'm thinking of the
Each time step,
not the time steps vary, so therefore the time steps to reach the goal. Therefore, he views this network, or at least the way he explains it in the video is, A, there is no input, and B, he highlights it as a difference of the fact that your output is fixed. The input varies typically. Normally, in this case, there is no input, but the size of these number of stages keeps varying.
okay.
You can run around for whatever you like, for however many steps you like. The BPTT is basically how often do we detach the gradient, right? So we stop backpropagation of the gradient in BPTT steps, but any RNN could be like forward pass can be done for infinitely many times. It doesn't depend on BPTT.
Yeah, that makes. But here, I think so. The criteria and the optimizer plus per step. It's Yep.
Isn't the angle an input, the steering angle that you give? That can change at each time step, right?
That of course changes at every uh, time step, because the control that we apply it on. So I think so. What they have done here is trained on that end-to-end RNN. So if we look at the where is the inputs that we have?
I think in this notebook he does not include the controller part. The interesting part he left out, I think. It's only the emulator.
Yeah. Yeah. There are a few other ways to solve this problem too, and this is probably the easiest way to get a initial understanding of what this problem is, and yeah, we can go through the code as well, uh, or there are, I think so, other implementations of this. Yeah, mm, you can have fun too. Yeah. But yeah, I totally agree. If we look at it here with respect to the controller part, yeah, this
It would
is
be
the
fun to implement this paper just from the paper without looking into any other implementations. Yes.
So this is the backward pass and the forward pass, as Arto has just alluded to. Ah. Yeah. Then if we look at the step one of training an emulator, we can add layers too, depending
Yeah,
on.
in his description, he says, okay, once you train the emulator, then it's kind of frozen. You just use it. The question I have is then when he also says that the back propagation happens through the emulator network into the controller, then the only does he simply mean that that happens because of the fact that the emulator generates the next position, or because if the emulator is frozen, there isn't any quote literal back propagation happening through it once the controller gives it the new angle. So once the new angle is obtained, then the emulator, all it has to do is output based on the current state, the angle, then output the new state. Now, if according to him, the emulator is frozen in the sense that, it's trained just on the MSC and generating MS, given an angle and a current state, it just outputs the next state. So then when he talks about back propagation through the emulator into the controller, what does he mean? Because other than predicting the next state, the emulator is not doing anything, right? It's like, um, in a coordinate, we freeze the body and only train the head. But in this case, it seems like we freeze the head, so to speak, which is the emulator, and all it needs to do, all we do is back propagate the next state, which is then used to train the controller, or am I missing something? Because I guess my question is, what is back propagation when the emulator is frozen after it has been trained? You don't really back propagate to the emulator, right? You just predict the next state and use that next state to train the controller. Is my understanding correct, or am I missing something?
Yeah. The thing is, this is the forward pass, and then this is the backward pass using the controller and the emulator. And if we if we go into the code, I do not see this thing happening here. The thing that
I think it
yeah.
says the weights of the emulator are frozen, right? So, like you said, Srinivas, it just, I mean, it's just, and I think someone has pointed in the chat as well. It just acts as a function. So there is no weight updation of the emulator during, I mean, of the emulator during the controller training.
Right. So then saying back propagation through the emulator is just saying emulator is used to predict the next state, like it's a function. So we don't really back propagate through it other than by generating the next state, which is what you use to then back propagate through the controller. Is my understanding correct?
Yeah, but emulator weights, the gradients which flow to the controller depend on emulator weights, because an emulator is a part of the whole function, right, of the whole network we are training. We don't update the weights of emulator, but it's still a part of the network we are updating. So the gradients computed they have to go through the emulator, and we feed back, basically, like if you imagine this backward pass, what comes out of the emulator backward pass goes to the controller. Or I don't know, does it make sense? Yeah, so what Renato is saying in the chat, that's basically what happens, right? So
but so that's where I'm still confused. So we compute the gradients, but then we compute the gradients of the emulator. That would mean that we are, but we don't change the weights and just pass through the various, whatever, the couple of layers in the emulator, and then, but don't change the weights of the emulator, and then use those gradients to feed back to the controller.
Yeah, I think thinking about GANs should give you a good intuition about this thing, right? When training a GAN, we iteratively freeze and unfreeze this discriminator and generator. And basically imagine now that your generator is being trained, but the discriminator is frozen. And again, you kind of back propagate the error through the weights of the generator while not updating it, and update the weights of generator. So basically what I'm trying to say is that the gradients, they depend on all the steps which happen in your calculation, right? It doesn't matter if your weights require gradient or not, but the partial derivative of the weights of the previous layer, which requires gradient, those still depend on the those partial derivatives just by the chain rule. They still depend on the next weights which come later in the forward pass, and so earlier in the backward pass.
Yep.
Right, but what I'm missing, Ato, in that, and maybe it's just having kind of running the code and looking at is you compute the gradient, but then you don't touch the weights of those two layers. That's what happens in the emulator during the backward pass. Is that correct?
Yeah. We just
We
do
use
not
those
update
layer.
the gradients, and we don't save the. We like don't need to store those gradients. We don't use those for update, but we still have to go through it to get the gradients for the controller.
I think so. We will have to take a look at the code, to get a complete understanding. But I do not want to be wrong here. So, this is the truck URL that you can find and go through the gradients that have been propagated. So even this is the way. How is it actually being propagated? Looking at this, the controller which is derived with the backward with the gradient here step. So you can see the architecture here, the actual implementation. Get the error from the emulator and add it to the input error for the controller, and this is being propagated. This is for the j equals I minus 1 to 0. So that's iterating through the, I think so here I represents the number of states that it has, the max steps, the max time steps. So that's what is going on here. Yeah, but you guys are right. I was thinking of the assumption after training, the back propagation that is being happening here, the training step with respect to dispatch update. So this is first they are taking the state vectors, then the steering angles, and then this is from a high level perspective. The this is on a truck emulator, and then for controller, as we have alluded to, these are the steps. We just take we just initialize it, those states, and then we use them to through the controller to the to give the signal to our truck, such that it can I think so. There was a stop that was performed on the emulator here, if I'm not wrong, to such that they do not propagate it to the emulator. Start fix emulator. What does this do? yeah, do not train the emulator. So the backward gradients are not pushed back here, and we only do it to the controller. So yep, you guys were correct on that. This is it. I think so. I will share this file in the chat too. Anything else, guys?
Yeah, I wonder if this task is really tough for like some classic controller, which would be like, I don't know, rule based or something.
Classic controller, rule based. Rule based. You mean to say handcrafted features?
Yeah.
I don't know. This is the second or third problem that I have looked in the control domain. So I'm completely new in the control domain. So
Yeah, because I just like intuitively, I think it's a pretty simple problem for like from classic control point of view, but yeah, that would be interesting to like explore a bit. On the other hand, this paper came out like in pre neural net era, right? So when neural networks were far from mainstream.
yeah, this was in 1990. I think so. Jan published his in 89, if I'm not wrong. Siemens. 1998. Sorry. So yeah, after this, this was before this 1992. I'm missing my timelines here, but yeah, this is a lot before the advent of deep neural networks. So this was kind of cool, and hence the you can see the notations here. They are a bit difficult to understand at first glance. This is based on the electrical and control theory. So I think so. With this, we end this chapter. These two parts: the week 10 of self-supervised with the trucker backer upper problem. That's all from me. Thanks, guys.
Thanks, Mike. Thanks everyone for joining.
Yeah, thank you.